In today's lesson, we're going to look at an absolute value. This one's a little more challenging. We have an absolute value inside an absolute value here. When solving absolute value inequalities, we want to identify when will the input of the absolute value be 0. So for this example here, we're going to focus our attention on the two absolute values. So the first question becomes when will this input here be 0 for our innermost absolute value? And we can see here we have these outer absolute value signs, and we want to know when will this input be 0. Let's do that first. Fairly easily, we can see with the innermost absolute value, you can see when x is 1, we will be taking the absolute value of 0. For the outer absolute value, we want to set the absolute value of x minus 1 equal to 0. Solving for this, we end up getting the absolute value of x minus 1 is equal to 1. And this gives us two values of 0 and 2. So therefore, the 3 points we want to consider on our number line is 0, 1, and 2. Let's take a look at these. So you can see here I've partitioned my number line into 4 intervals, focusing our attention on interval 1 here. Subbing in any number greater than 2, you can pick a number inside of here. Let's say we sub in a 3. This expression will be positive, and this as well will be positive, which means we can drop the absolute value and solve the following inequality. You'll notice here I was able to drop the absolute value of x minus 1 without adding a minus sign, and likewise the absolute value of the entire expression I was able to drop also without adding a minus sign. Recall here that the absolute value of x is either equal to x when x is greater than or equal to 0, or negative x if x is less than 0. So in this case here, x minus 1 was positive, so I could drop the absolute value without adding a minus sign, and then the entire expression was also positive, so I could do the same. Solving for this here, we get x is less than or equal to 3. That is inside of this interval, so we're bounded from 2 to 3, including those endpoints. Let's take a look at interval 2. All right, now we're going to focus our attention on the interval from 1 to 2 now. So looking at the interval from 1 to 2, we can see that if I were to pick a point in this interval, let's say we were to choose 1.5, subbing a 1.5 into here, this will yield a positive as the input for this absolute value. So we can drop the absolute value here at no cost. I won't have to put in a minus sign on that. However, when I put that 1.5 into this expression, the result here will be negative, in which case we can drop the absolute value, but it will cost us a minus sign. Doing so, you can see here we end up solving the inequality. I end up getting x is greater than or equal to 1. So again, that's x is greater than or equal to 1, but within the interval from 1 to 2. So the answer set is going to be bounded between 1 and 2, including the endpoints there. So now we have our answer for interval 2. Let's take a look at interval 3. Examining interval 3, we're now in the interval from 0 to 1. Picking a number between 0 and 1, let's say we were to pick a half. This will be negative, in which case we can drop the absolute value. We'd have to tack on a minus sign there. And the difference between this and this will also be negative. And again, we can evaluate this, but we'll have to drop the absolute value, again needing a minus sign. Doing so, we get the following. And solving for x here, we end up getting the inequality x is less than or equal to 1. And again, that is within this interval from 0 to 1. So the answer set for this becomes square bracket 0 until we hit 1, again, square bracket. Let's take a look at interval 4. Examining interval 4 here, you can see we're less than 0. And again, if you pick anything less than 0 here, we can see that the x minus 1 will be negative. So we can drop that absolute value, and that'll cost us a minus sign. However, the difference between the absolute value of x minus 1 and 1 will be positive. So I can drop the absolute value sign on the outside absolute value without having to multiply by minus 1. Doing so gives us, solving for this, I end up getting x is greater than or equal to minus 1, and that becomes our answer here. So now we're going to have x is greater than or equal to minus 1. Again, it's within the interval less than or equal to 0, so this is going to go from minus 1 all the way up to and including our 0. Combining together our answers, we have 2 to 3, 1 and 2, 0 and 1, and minus 1 and 0. So the answer set to this is going to be the interval from negative 1, including that minus 1, all the way up until we hit 3, and a square bracket on that 3. Let's take a look at a graph of this function and see a visual representation of this solution. So if we examine the function here, the function in red represents our absolute value of the absolute value of x minus 1 minus 1. Right? So what this represents in red is the following function on the left that we are working with. And you can see here graphed in blue represents the line y equals to 1. So the question was asking, when is our function in red less than or equal to 1? So essentially we're asking when is that equal to 1 or below 1. So where do we see that happening? Well, we can see the function itself is equal to 1 here, here, and here. And the function is less than 1. All of these values that we have here that we are highlighted in black. So you can see here that where is the function going to be less than or equal to 1? We have this point here which represents -1, and this point here which represents 3. And if you remember, that was our answer. It was bounded between -1 and 3, including those endpoints, and we have that here. To graph the function that we have here in red, i.e. to graph this absolute value of x minus 1 minus 1, going back to the intervals we have created previously, we'll see our absolute value function decomposes as follows. And we can see here that when we look at the interval less than or equal to 0, our function becomes the line y equals to -x. Between 0 and 1, our function becomes the line y equals to x. Between 1 and 2, the function becomes the line y equals -x plus 2. And then lastly, greater than 2, the function becomes the line y equals x minus 2. And we can see that graphed here, each one of these here. This represents the line y equals -x. This is the line y equals x. This is the line y equals -x plus 2. And this is the line y equals x minus 2. So this is an example of a more challenging absolute value inequality. Thank you.